Thanks for making it out today. So this is the first of our two theory days. And today it's a packed day. We have a bunch of wonderful speakers. All of you are have a lot of different backgrounds, cognitive science, neuroscience, some of you maybe machine learning and computer science, but today we're going to be talking about some broad principles of learning and trying to understand how and why deep learning works. But this hopefully will also have some broader implications for general principles of learning as well. And we have speakers from a wide variety of backgrounds: statistical physics, neuroscience, machine learning. So hopefully you'll get to hear a bunch of different perspectives on the theory of learning and why does learning work the way it does. We'll start off with Tomaso Poggio here. All right. So let's start off with Tommy.
Thanks, Akshay. Can you hear? I'm too loud? No? Okay. All right. So I'm Tomaso Poggio, and I'll speak about the general framework of machine learning, and especially a part of it which is usually neglected, which is approximation theory, and end up with some conjecture about transformers and large language models. So, first of all, people have contributed in various ways to the work I described are here. Several of them are in the audience now, almost all of them, 90%. Now, first question, which is, I think, a general point about these 2 days of learning and about machine learning in general, is that theory, I think, is important and has been neglected. And I don't mean theory in the sense of formal proofs that too often, pepper theory papers, but I mean theory in the sense of understanding principles underlying machine learning. It's a bit in the sense of physics. What are the basic principles that are at play, not the details or derivation of theorems. And I think there is a good example in history about theory taking some time to develop after the initial discovery. I think there is a pretty good analogy with deep learning. And the analogy is with Alessandro Volta, who of course discovered the pila, which in Italian means a pile of stuff. Pila because there were, I have at home a faithful copy of this, which are discs of copper, zinc, and wooden, and you put water on it, and you will produce 2.1 volts for about 4 minutes, after which you have to disassemble, clean up the oxidation, and start again. Now, this was essentially a random discovery. The motivation for it is a typical one for an academic. He was professor in Pavia, which is a university town close to Milan. And he wanted to show that a colleague of his, a professor in Bologna, was wrong. So typical motivation. Galvani said electricity is of biological origin, and so Volta built this thing without any biological component and produced electricity. Now, why it's important was the year 1800. So Napoleon made him a count because of the discovery. And until 1800, in the world, information was traveling at the speed of a horse. After 1800, information traveled at the speed of light. Volta himself designed a telegraph line between Pavia and Milan. And so it was a major development. What happened was that until then, people did not have access to electricity, continuous source of electricity. There were only sparks. So this was the first time people could study electricity, continuous for a few minutes. And so that started the revolution. Within a few years, all electrochemistry was done, electrical motors started, electrical generators, and so on. But for the next 60 years, nobody really understood what electricity was. So there were these development applications, no real theoretical understanding. It was only around 1860, 60 years later, that Maxwell came up with a theory of electromagnetism. And then many more things happened after that, including radio and telephone and radars and solid-state electronics and computers and the internet and so on. So it was a major thing. By the way, there was a celebration in the year 2000 for the bicentennial of the Pila, and I sat for lunch next to the Countess Volta, the grand-nephew of Alessandro Volta. So it was not too long ago, a few generations, 200 years ago. Okay, I think it's a similar story with deep learning. It was more or less a random discovery. And we still don't have a theory. We are in between Maxwell and Volta. But having a theory would be great, right? Does not forbid, not having it, we can still have interesting applications, and we do. But it would be great to have one. And there are some very good reasons why we want it. A theory, one is that we want even better systems than large language models or ChatGPT or so. And then, people speak about explainability, but I think the real explainability here would come from a theory. We don't ask a plane to explain why it crashes. If we know what the instruments say, we have a full theory that explains what has happened. And so for many technologies where we have a real theory, we don't have those instruments or tools to explain to us in words what's going on. A theory is a much better explanation. It's funny that nobody mentioned this when all the many discussion about explainability and fighting risk and so on. And another one is the hope that there are general principles, fundamental principles of intelligence. And if that's the case, then discovering them would also help us understand better, eventually solve what is, I think, the greatest problem in science, which is understanding the human brain and the human mind. That's a real one or many Nobel Prizes. Okay, and I found recently, like yesterday, that there is an interesting blog, you should try to find it, by Misha Belkin, in which he makes a very similar point. It looks like he almost, looked at my slides, and it's about the importance of having a theory, that a theory should be possible for these systems despite their apparent complexity, the existence of fundamental principles for deep learning and learning. And he also mentioned that one of the puzzles is the curse of dimensionality. I will get to that in a second, and how this modern, very large network avoid that. And understanding of this would be one of, may uncover some of the fundamental principles that machine learning is using. And the main conclusion is that understanding the fundamental theory of deep learning and applying its analysis to real systems is a compelling and urgent need. So I encourage you to have a look at that blog. And so let me start with this. This is a very simplistic view of machine learning, and I'm sure you know a lot of this, but the basic framework is not the only one, but I would say it's a basic one because you can use it in various ways, also in semi-supervised learning, and similar thing is the supervised learning problem, where you have a set of training data that define in an implicit way a mapping, a function from your input to your output, this f mu, and the goal of learning theory is to have a representation, an approximation of this unknown function, given the data, okay? So the basic approach, I'll mention a different one shortly, but is you are looking for a function that has parameters, a parameterized function, like you could think of a linear model, you could think of splines, you could think of a kernel machines that can approximate a broad range of possible function f mu, given the data, and where you can optimize the approximation by minimizing how close f is to f mu by turning the parameters, like the weights or the coefficients. Okay, that's the general framework. And so first you need to decide what is your space of parametric functions. And for a while it was one-layer kernel networks, like radial basis functions. And more recently, there were deep networks, so multi-layer with RLU or similar nonlinearities. And this space of approximating function, so you have a target function, which is the unknown one, the f mu, and you want to have an f with which you approximate this unknown f mu. So this is a question of approximation theory. Find a space of approximating function that can approximate a very large class of mapping from input to output. Once you have that, you can optimize the value of the parameters by minimizing some error, like the square error between the approximating function and the target function. And then you can study, if you want, generalization properties of this, how well the function you have found is doing on new data. Okay, and of course, one of the conditions that you want in this parametric function, in your approximating function, is that they should have a non-exponential number of parameters. Non-exponential, for instance, the dimensionality of the function, because otherwise you cannot compute them. So from the point of view of approximation theory, it was known for a long time, since the 80s or so, and this was part of the reason why in the 80s people looked at one-layer network and not multiple layers mostly, is there is this result that says one-layer network, like radial basis function or like RLU, but one layer, can approximate any continuous function on a compact interval arbitrarily well, giving enough parameters. And if you have multiple layers, the situation does not change. So why, from this point of view, there is no point in having multiple layers. However, to realize later that, yes, you can approximate a very continuous function arbitrarily well, but the number of parameters you may need can be in the order of epsilon is the error you're making in the approximation, say in the sup norm, maximum error, it's to the minus the dimensionality of the function of many variables divided by how smooth the function is. And so, for instance, if suppose that m is 1, you have just first derivative, and so the function is not particularly smooth, but suppose that D has a dimensionality of CFAR images, which is roughly 1,000 pixels. Yes? Well, M is essentially a measure of smoothness, which is like, number of derivatives that are bounded. Well, for RLU, this does not apply because it's not smooth, but take a GELU, it's fine. Take an RLU which is, smooth around the corner. And there are other ways to prove this in the case of this continuous function. But the name to look is Yarotsky. I can give you the pointers. Anyway, so for CFAR, assuming that the function mapping, say, CFAR images to classification, which whether it's an image of a face or not, for it's a binary classification, this function may need, and you need, say, an approximation of, say, 1/10, so 10% error. You have 1,000. You have number here which is 10 to the 1,000. Now, 10 to the 1,000 is a lot. Do you guys know how many protons in the universe? Yeah. So much, much, much more than, our universe. So that's a real, it's not just, it's a real problem. It's a real curse. It's the curse of dimensionality. And the way you prove this is you can imagine that you can expand the function in a Taylor series or representing as a polynomial, and you'll see that the number of terms and therefore the number of parameters grows exponentially with the dimensionality. You can try to discretize the function. Imagine you discretize every variables in 10 values, and then you have 10 to the number of variables, which is 10 to the 1,000. So, and there are proof that all of this is equivalent, and you cannot do, this is the best you can do if you look for techniques that have certain regularity conditions. So that's a real problem, and typically in the past people have looked at countering this by considering functions that are more and more smooth. But of course this often, depending on the situation, seems like not true. So, on the other hand, we have this puzzle that neural networks do very well and with large dimensionality. So why? So this was, so a few years ago, we found a class of functions that seems to, it does avoid this problem. And these functions are functions that are compositions of functions. So if I have a function of a function of a function, and so think about a binary tree, that's one example. Each node is a function of two variables, and so this is a function of the outputs of these two functions. And so this is also 2 variables. So I have a function of 8 variables composed by function of 2 variables. It's a function of composition. Okay, it's easy to see that, relatively easy to see that if you have a situation like this, the parameter that counts as a dimensionality is not 8 for the curves, but is 2. So if you have a compositional function, what count in terms of the curves of dimensionality, determining the number of parameters, is the dimensionality of the worst constituent function, not of the overall function. Notice in particular that I can make the number of variables in a composition like this as large as I want. If I increase the number of levels as a logarithm of the dimensionality. Okay, so that's one way to avoid the curse of dimensionality. And if you want, at the end, the proof is very simple. It's just that errors don't accumulate, don't explode exponentially. We can go through it later. And you can generalize that to an arbitrary graph. In other words, you have a function graph that represent how the function you're trying to learn can be represented in terms of compositions of constituent function. And so in a graph like this, the curse of a dimensionality in this case is not 9, which is the total number of variables here, but is the constituent function that has the largest number of inputs, 4. A few things. When you have a compositional function, the compositional representation is not unique. You may have multiple representation in terms of composing function of the same function. So it's not unique. But in general, this assumption, I thought for the last 6 years that this hypothesis of functions that are compositional and can avoid the curse of dimensionality is a strong one. The most functions are not compositional, I thought. And so, and Max Tegmark, a colleague of mine at MIT, also had similar feeling, and so we came up with why compositional function may be important for humans or for applications you are interested in, and so on, like vision, where it makes some sense that you don't need to process all the pixels at once, but you can compose processing patches of images and patches of patches and so on. And by the way, part of our result was that for functions that are compositional, a deep network with the same function graph can do approximation without curse of dimensionality.
Just as an assumption, if we have a node after the next layer that has more dimensionality than the original input feeding into one node, would that become the max dimensionality node?
Well, yes, it's difficult to, I don't think you can have more higher dimension in a node than the input dimension, right? But you could have the same, but in that case you don't gain anything. So what I'm speaking about is really sparse compositionality, where the constituent function have a small number of variables, usually much less than the dimensionality of the compositional function. Yeah, skip connection. Yeah, skip connections, good point. We can come to this later, but skip connection is like creating compositional network, but of different depths and different configuration. You can essentially expand the skip network in a sum of networks. So it's a bit more complicated, but the story is the same for each one. Here I don't assume a skip connection, but you can adapt this result to the skip connection case. Yeah. So if the graph you implement in a network is different from the graph of the underlying function. Yes, so this is a good question. Let me leave it aside for a moment. It's basically, empirically, if the graph is similar enough, things will work. But the reason I'm not answering exactly is because this is, I'm speaking about approximation theory, and this is kind of existence results. The next question is a big one, is optimization. Suppose you have a network that has a graph which is larger than the one of the function you are trying to learn. Can optimization find which connection should be put to 0 or not? Suppose the graph of the function we are trying to learn is a subgraph of the graph of the network you're using. In principle, optimization may find the correct graph by putting weight to 0. These are open problems. I cannot answer this. There are empirical and theoretical evidence that this may be a problem with L2 minimization, and much less, perhaps not a problem with L1 minimization. Does everybody know L2, L1? But let's come back to that later. So the answer is, in fact, for me, what's surprising is not because, like in physics, you'd say function should be compositional because in physics, interactions are local, and so from this you can infer sparsity of constituent interaction. There could be an argument about neuroscience and evolution saying, well, our brain has evolved to have short connectivity in cortex, and then this is the ideal architecture to deal with sparse compositional function, and so these are the things our brain can do, and these are the things we're interested in. But the real answer seems to be more general. Basically, every function is compositionally sparse, in a certain sense. So these are definition, a compositional function with sparse of the variable is a function where there are constituent functions that depends on a small number of variables, small enough. That's the definition. Now, another one that's jumping to something else, computer science, is that I define a function to be Turing computable if there is an algorithm such that I can compute the function on a Turing machine. Okay? And essentially, you have a Boolean function that the Turing machine is computing, and this Boolean function must be an approximation as good as I want of the function on the reals that I'm interested in. Okay, and I called efficiently computable if it's computable by a Turing machine in polynomial time. So to me, these are says these are, realistic functions. Okay, and so the kind of surprising results is that if you have a function on the reals that is Lipschitz continuous, for instance, as bounded the first derivative, then compositional sparsity is equivalent to efficient computability. And that has the corollary that for every such efficiently computable function, there exists a deep network with sparse connectivity that can approximate it arbitrarily well.
Are there any constructive improvements?
It's not a
the minimum need like the highest degree of compositionality?
Yeah, you can get them, but in this statement, it's just an existent.
Are there cases like this?
Yes, there are some. Yeah, a simple. I think Santosh Vempala will speak tomorrow. I think. Sorry? Sunday. He's the one who gave me the initial idea, because a Turing machine is essentially composing sparse function in the read and write operation. But another way to think about how to prove this, can prove it in many different ways, is to think about, suppose that a function is Turing computable, then it means that I have a Boolean function that approximates it. Now, if I have a Boolean function, I can always, it's equivalent to a Boolean circuit composed of AND and NOT gates, possibly with many inputs. But then I can replace any one of these gates with a little binary tree, including AND and OR gates, sparse. So I go to sparsity, compositional and sparsity by this argument.
Yeah, you should want to have a sort of formulation in which you would know the number of parameters you would use to describe this function.
Yeah, right. Basically,
because you don't want to have any everything binary, because that might also require still a lot of parameters.
Yeah, it turns out that essentially you can, one limitation is how many layers or levels you may have. And this cannot be larger than the log of the number of layers, the dimensionality. So that essentially says that a deep network, that by the way will have sparse connectivity, can deal with every, I would say, practical function. Practical in the sense is a function that can be computed in a non-exponential time. Yes?
So can I ask, so when you talk about compositional sparsity, you mean with respect to a given basis, the x1 up to xd?
Yes.
Right, so but then there's the question of, if I told you there exists a basis for RD with respect to which your function is compositionally sparse, finding that basis could itself not be an efficiently computable thing. And so there's still kind of like a gap in a sense.
Yeah, there is a gap. The gap is the optimization part.
Right.
Yes, good point.
The previous slide, when you spoke about the efficient computability, so you can find the function in polynomial time. Is there some assumption on what sort of search strategies we're using, or is it just
is that an assumption?
on the kind of search strategy that we use for the function? So is it like backprop versus some other algorithm for the function, or for finding the exact?
Well, this is not really about learning, but really computing the function. If you know, yeah. So
it's independent of the actual optimization used to.
Does not involve. This statement is not about optimization. It's really computing. Suppose you are given this function. How long does it take to compute it? If the number of units or layers would be exponential, even if they're compositionally sparse, it will take forever, right? So I don't want that. So anyway, I was surprised by this. I don't know if you are surprised or not, because it's between obvious, almost tautological, and surprising, and I cannot decide. So these are restating essentially what I just said, and in a certain sense, this means that if you could, for the unknown function you are trying to learn, if you could say what the graph is, which is sparse, you have basically solved most of the problem. And in a sense, that's what happened for convolutional networks, right? You're basically assuming, I know the underlying graph is convolutional, so each unit just has this sparse connection to a small number of pixels and small number of units. So in that case, I'm assuming I know the graph, and then I do optimization of the parameters, and to me, that's one of the reasons why convolutional network have been, before transformer, have been the most successful architecture. You can argue empirically that multi-layer, densely connected networks usually are not better than standard techniques like radial basis function or so, but convolutional networks are much better. So, and transformer is a separate story, and I'll get into it. So this is this question about, you asked about skip connection. Skip connection is really essentially combining. There are more skip connection in general than the one drawn there, but as an example, you know, you're having, in this example, you're having not only the network with all those layers, but also a network with just one layer because it goes to the output, and so. So that's been interesting things to explore in terms. So I want, so if all of you know the standard deep networks with RLU or GLU, very simple operation. Each unit is submitting a lot of inputs with their weights, and then the nonlinearity, what the neuron does is just the rectification of the RLU. And you're doing stochastic gradient descent, so typically, or gradient descent, to find the best value of the parameters that minimize the error on the training set. Okay. Now, there are, of course, dense architectures, and for some reason, theory papers have been focusing on dense architectures. For instance, Rademacher complexity, which you use to estimate how good generalization is. Most of the many results are for dense networks. But convolutional architecture are usually sparse. And by the way, this is not because of convolution. It's because the kernels of the convolution are small, typically. Like for images, 3 by 3. In a lot of things I would say, convolution, the actual operation of convolution does not do much. The important thing is that the kernel is short, so to speak, is small. And so if you think about, how many of you know what is a Toeplitz matrix or a circulant matrix? So this circulant matrix is a matrix that essentially reflects the properties of convolution. In a network, this will be the weights in a convolutional layer when you join the end of the layer with the beginning. So it's circular convolution. Tuplets is when you don't do that, and so at the boundaries you have some stranger things happening. But the main point I want to make is that you look at a Toeplitz matrix corresponding to a convolution in networks, today networks, that matrix is very sparse. Lot of zeros, because the kernel is short. And that's the important point in many of these properties, especially sparse compositionality. Convolution, which is weight sharing, plays a role in making the number of weights smaller, but is not what it makes, counter the curse of dimensionality, not at all. It is the locality of the kernel.
So, going with the example of the sparsity, right? Or not the example, but the theory of sparsity. If I'm understanding this correctly, the number of channels you get from the convolutional operations must also be limited to a certain extent to be able to call it a sparse network, right? So it doesn't make sense in this context to have too much dimensionality.
Yeah. Right? Absolutely. Yeah. Okay. So, for instance, in this binary graph, the result about the fact that you escape the curse of dimensionality is true even if that network, that function is not convolutional. So convolutional would mean that the red dot, let's see, this red dot is the same function as this one, as this one, as this one. This is weight sharing. But you get this avoidance of the curse of dimensionality even if they are different. What matters is each one has two inputs. Now, having weight sharing decreases the number of weights, but not in an exponential way. Yeah?
In real brains, like how is there, like the individual
Real brains.
Yeah, in real physical brains, like what are the input connections? Like what is the compositionality there?
Well, if you look at say cells in the retina or in V1, you have mostly local connectivity. There is no reason, no biophysical mechanism that can give you the shared weights automatically, like you do in a neural network. You impose it during learning. What may happen is that if each of the unit cells in V1 are exposed over time to similar patterns, then they will become similar. And so the fact that you have potentially shared weights come during development, not imposed from outside. But nobody knows whether you have same weights or not.
Is there a sort of estimate you could give? Indeed, I agree that there might be regions which sort of will get the same weights, since it gives sort of similar output on a certain input. But could you sort of give an idea of an approximation to what the compositionality would be in the end of the cells within the retina or support? I mean, it will not be binary, like I said, like typically neuron gets like thousands of inputs.
Yeah, let's see. It seems you have in V1 in monkey humans, you may have. Let's see. Speaking about ganglion cells, you look in the center of the fovea. You may have just one input, one photoreceptor per ganglion cell, and increasing towards the periphery. So it's not a fixed number. So another architecture is what we spoke about, the residual architectures. Here really the idea is that you, instead of trying to learn the input-output mapping, you are trying to learn the input-output mapping f of x minus x. So you start assuming that there is a linear component in the output. And that has a lot of good properties, also from the point of view of approximation. And so essentially, what is happening is that you start with a simple, say, linear term, and then you look how much of the error this is catching up, and then you are trying to fit some more complex nonlinear stuff to the residual error, and you proceed in this way. And this is a technique that has been used for many, many years. There is another interesting result I found that it's essentially says that if you want to have good classification for different classes, you have to have the first layer to be more wide than the input layer. So this is kind of in support of what is often found, that the architecture of deep networks is often, you have an input layer, and then you have a bigger intermediate layers, and then you go down to a small number of units in the layer close to the output, possibly the number of classes. So this kind of wing shape. Input on the left, output on the right. Okay, so said you have this property about for all compositionally sparse, you can approximate without curse of dimensionality, and then there is also some separate result on generalization that seems to be completely separate, but are in the same direction. So let's see. Axel will speak about a specific class of deep network models with RLUs, and so I'll not get into the details, but he will tell you more about it. But the bottom line is that you start with the usual gradient equation on the W parameters, the weights, several layers, RLU. You have a normalization, but it's not batch normalization, it's weight normalization. People know about the normalization. Anybody does not know? Raise your hand. That's no problem. You will not be scolded for that. Anyway, so the normalization is you normalize the weight matrix at each layer to have a Frobenius norm 1. So the sum of the squares of the elements is 1. And then you have rho. Rho is a number which is the product of the norms of all the layers. And so we have a regularization here that depends on lambda, and here is the product of the norm of each layer. Typically, people have a regularization that is the sum of the norm of each layer. But if you are normalizing each layer, it does not make sense to have the sum. So, and there is another deeper reason why the product is a good idea. So that's something not usually used, but there are deep reasons for using it, and it seems to work well. Because the RLU is homogeneous, this has the property that if I take the function, which is the network, with normalized weights, I have some f of x. The d here represents the RLU that depends on x, from layer L to layer 1. And the actual network output will be the output of the normalized network multiplied by rho. Okay, and in this case, the loss function will have some shape. This is not real, it's just conceptual visualization. But you can think of being, for rho equals 0, you are in the middle, you have a loss function, which can be very non-convex. And then there are regions where you have 0 loss. You are interpolating the data. And then the norm of rho has to have a certain values in order to reach, cannot be too small in order to reach interpolation. So we know that from a couple of theorems some properties of this landscape. One is that without regularization for deep networks with smooth RLUs, there exists 0 loss, and these 0 loss are degenerate, highly degenerate, meaning that there are many values parameters that reach this 0 loss. It's not unique. It's like a flat surface. Yeah.
When we talk about the efficient computable systems that are equal to just, when we talk about the efficiently computable systems, when we compare them to sparsity and compositionality, when we say smooth curve, does that relate to continuity, or is it a smooth loss function? Like continuity versus discrete functions where there's just gaps in.
Yeah, it refers. So it refers to a smooth loss function. So for instance, the RLU, the standard RLU does not fit that. So that's why I said smooth RLU. I think this is a technical issue that can be solved, but the theorem is stated, this theorem is stated for the smooth case. And so the dimensionality of the zeros is very high because it's the number of parameters minus number of training data. So for instance, CFAR, typically you may have a network which is 200,000 parameters, 1 million parameters, you have 50,000 training data. So this would be, 200,000 minus 50,000, the dimensionality of the 0 loss, huge. N is number of data.
Yes, but why would the number of parameters be M instead of W?
Well, I call that effective parameters. Forget that part, but it's like, because all the other ones are degenerate. You cannot get free parameters, parameters that are effective. If it's like saying in a system of linear equations, it's exactly the same. You have if you have a system of equations and you have n equations and you have w parameters, you just need n parameters for finding the unique solution of the equation. But everything else gives you degeneracy. Anyway, that's probably not a very helpful sentence, so delete this, please. The key part is this, which, by the way, also explains, in some sense, it does not explain completely, why optimization is easy. It's because the volume of the zero in parameter space is huge. Okay. Now, yeah, this is an explanation why people typically use this for regularization. We are using this. The main reason, there is homogeneity, but there is also this argument. I'll come in a second, which is that that there is a complexity bound that depends on this, it turns out. So if you want to control the complexity and therefore have a small generalization bound, a small generalization gap between empirical and expected error, you want to control the product of the Frobenius norms. Yeah.
The degeneracy you told us about on the previous slides. So this would be lifted if you would add something in the loss function like weight decay or.
We have weight decay.
This was a statement with weight decay.
Regularization means weight decay. Really, it's another name that, often in the neural network community they give new name to old things.
But the statement of the degenerate manifold of global minima, this was with regularization.
Oh, no, the theorem I shown before was without regularization.
That was without,
yeah.
Yes. And so if you do it with, then...
Good question. So, so this was a question that I asked in my class last year, and the answer is that in this case, which is unrealistic, you have a different regularization parameter for each one of the layers. Then you get isolated minima. The function is so-called Morse. But in this case, it's not clear what's going to happen. However, in this case, the one we are using, we have the generate minima, also with the regularizer.
Can I ask maybe a stupid question about the homogeneity? So I would have thought that you shouldn't square the norms. Like, a depth L network is homogeneous of degree L, but now your regularizer is homogeneous of degree 2L. If you square everything, so, I'm just kind of like, I'm not sure what...
Well, the typical regularizer is, W square, right?
Sure. But I mean, like...
and W square would be rho square in our definition.
Yeah, sure. I agree. I'm just saying, if you had a one hidden layer network, using rho squared kind of makes sense, because if you multiply all the parameters by a constant, the network output gets multiplied by the constant squared, and so does rho squared. But then when you go deeper, it breaks down. But if in your definition you removed the two, then you would maintain the property. Everything would be L homogeneous instead of one thing being L homogeneous.
Well, the homogeneity comes from RLU, right? And,
yeah. Right. Mm-hmm. So I'm just asking, do you really want the square there in your regularizer? The product of the squares instead of just the product?
Well, I think in the simple L2 minimization framework, yes. Now we can discuss, L1 minimization, and there is, but that's an interesting separate story. So it's a good point, but this would be, the kind of standard thing that people have been. So this is a summary of these topological theorems about. There are a number of projects that may be interesting. I can tell more about the optimization question. But 5 minutes. So let me skip these Rademacher bounds and basically I'll tell you that if you look at Rademacher bound for those kind of networks, there are two things that are important. One is rho, so it's the product of the norms. The smaller rho, the better the bound is. So small rho means small complexity, better generalization error. So this essentially says you have an infinite number of parameters that give you zero loss. Among them, choose the one that give you smallest rho, which is exactly the same you do in the linear case with the pseudo-inverse. Only that there is the norm of the pseudo-inverse, here is the product of the norms of the various layers. That's one. Yeah.
Smallest norm, like L2 norm or L1 norm?
L2 norms. Then, and if you do this, bounds that, if you use the standard formula for dense connected network, or you use VC dimension, the bounds you get on CIFAR are something like 1 million for the generalization error, when you should get something between 0 and 1. But if you use what I said, the sparsity, you get something which is not between 0 and 1, but in some experiment we did, it's close, it's like 5. So sparsity in the weight matrices, in small rho, and then sparsity in the weight matrices gives better bounds. Many order of magnitudes better than. With a paper of several of these things, and Akshay will speak about it. Okay, so I wanted just to mention this. This is now what I told so far should be true, all of it, but this one is more like a conjecture. Is if you believe that sparsity is important, compositional sparsity, then a natural assumption is that maybe transformers, this is the original paper, 2017, maybe transformers are involved in finding the sparsity at each level when you don't know it. When you assume it's convolution, you know it. But suppose you don't know. The idea is then that in a standard convolution network, you assume that each unit gets, say, 3 by 3, whatever inputs. You know the graph. And it's sparse. In transformers, you have each unit as an attention mechanism. This attention mechanism is looking at all the tokens and essentially deleting a lot of them, keeping only a few, or selecting only a few. And in particular, it selects the ones that are most similar according to a measure of similarity which is learned during pre-training. So the idea is that this mechanism is really trying to find among all the dense connection a small number that are actually fed into the RLU module. And there is evidence that the attention mechanism does give you sparsity. It would be nice to have some more such evidence. And there is some other, so that's the main message. I can stop here, but I just mentioned many years ago we had some work with Federico Girosi about what we called hyper-BF. This is like radial basis function. This could be a Gaussian or a Laplacian depending on the distance from a data point and the center, which is, a data point would be a center. Each data point is a center, and X is the new input. And so there were two modifications to this basic classical radial basis function scheme. One was to replace the Euclidean distance with Malanobis distance. So you have a symmetric matrix here that you're learning. And if you think about the diagonal such matrix, it essentially weights the different features, the different components of the vectors. Think about it. These are vectors. So a diagonal matrix here will, if it has an entry which is 0 in the diagonal, the corresponding component in the vector will be set to 0. That feature does not matter. And you can also learn the center themselves. Instead of being data could be a smaller number of centers, and you can learn all of this through gradient descent, in principle. Now, recently, Misha Belkin again has done this part, rediscovered this, and he claims that one-layer network with this Malanobis distance does as well or better than neural networks on tabular data, not on image data, tabular data. P of X? Oh, this is a polynomial. This is simply, for certain kernel, you need a polynomial because the null space of the kernel has polynomials. But in general, for Gaussians, for you can forget it, you don't need it.
We learn W this network. We learn W.
Yeah, the W is learned by gradient descent, for instance. Misha has another interesting technique to learn it, but in our original equation here was learned by gradient descent.
I had a question about some previous slides about sparsity. Is this sparsity in the ambient dimension or the intrinsic subspace?
It's sparsity in ambient dimension, but the ambient dimension can, of course, be changed by a linear transformation, right? So it turns out that self-attention is essentially doing this. Self-attention, you can write it as this way softmax, but then you can, if you assume that this Q and K are norm 1, then it becomes this, which is an hyper-BF with a non-Euclidean metric, which is given by essentially this. And in addition, has another interesting property. It's normalized. And so these are called kernel regression in the Narandan-Watson regression in the kernel literature, old stuff. It's like having a kernel approximation, but with normalized kernel, norm 1. And the nice property of those kernels is that instead of being f of x equals sum of C alpha and then the kernel x, where the C alpha have to be found typically by linear inversion, but by computation. The C alpha now Y alpha are exactly the target. So you don't need to do any calculation to do the training. They interpolate. And so that's why you can do in-context learning in transformers. You don't need to run any optimization on the prompt.
Well, to get interpolation, the kernel needs to be singular, right?
Well, that's a normalized kernel.
Right, but you won't get exact interpolation unless the diagonal dominates.
Well,
So
but
your kernel
with the
length-
normalization, you can check that it does the
Oh, really? You'll
yeah.
get that when you do. Oh, okay.
Yeah.
I didn't know that.
Yeah, we used this hyper-BF once. This is just fun, and then I'm finishing. Many years ago, 93. So at the time, we did not use pixel. There was an automatic system extracting feature from faces. The problem was distinguish male versus females, learn to distinguish. So we used an hyper-BF network with centers and and Mahalanobis distance. Based on these 18 features that were extracted automatically from the images, distance of eyes, eyebrows, and this system on, 50 or 80 examples. These were the times in which you find that there are a few important features, 1 and 2, and they were for distinguishing male from females, and they were, the most important I think was the distance between eyes and eyebrows. It's probably a consequence of makeup, And then learning the center, which is learning the cluster of male and female, give you essentially caricatures of a male and a female, so exaggerating the differences. Anyway, this last part has nothing to do with, it was just a historical remark. Let me finish. I think, let me see if I have something left, but I think I said everything, and if you have other questions, ask them.